Hi, geometry scholars. We are starting a new section today called the tangent ratio. And we will go on to other ratios, but the first thing you have to understand is it is easiest to use the tangent ratio when solving real life problems. The tangent ratio, in a nutshell, is when you take an angle and you write the length of the opposite side over the length of the adjacent side, and we call that tangent. It's just the name of a ratio. Okay, so in this section, you're going to learn what tangent ratio is. We're going to talk about angle of elevation and depression, and hopefully you'll find how to solve those real life problems. Okay, so here we go. A trigonometric ratio is a ratio of the lengths of two sides in a right triangle. All right triangles with a given acute angle, so the smaller angles, not the right angle, are similar by the AA similarity theorem. That's theorem 8.3. So we know that in this diagram, triangle JKL is similar to triangle XYZ. And you can write KL over YZ, so the side over the side, is equal to JL over XZ, the bottom over the bottom. You can also rewrite that as KL over JL equals YZ over XZ. So you can do side over bottom equals side over bottom. That's also a trig ratio. So trig ratios are constant for a given angle measure. The tangent ratio is a trig ratio for acute angles that involves the lengths of the other legs. So we're going to define a couple things. You always know that the hypotenuse is across from the right angle. Well, then we can talk about the two other legs. So we specifically want to talk about, we'll look at angle A. If it's connected to angle A, we're going to say that's the leg adjacent to it, meaning it is connected. If it's completely not connected or across the triangle, that leg is going to be called the opposite. So that's opposite angle A. So if we wanted to write what we're going to call the tangent ratio, we've got this triangle with acute angle A. The tangent is written as the tangent of A is equal to the length of the leg opposite angle A divided by the length of the leg opposite angle adjacent to angle A. And so we could write BC over AC. And we're calling that the name of tangent. Anytime we write a ratio in a right triangle like this, they're called trigonometric. And we'll get into that a little bit later. We usually shorten it as trig. So these are trig ratio called tangent. There's more later in the chapter. This is how you use it. In the right triangle above, angle A and angle B are complementary, so they add up to 90 degrees. We know that about right triangles. So angle B is acute. You can use the same diagram to find the tangent of angle B. Notice that the leg adjacent to angle A is the leg opposite angle B, and the leg opposite angle A is the leg adjacent to B. So it depends on which angle you're looking at. That's why we need to know which one's connected and which one is across the triangle that's not connected. So we're going to go ahead and do this example.
Find the tangent of angle S and the tangent of angle R. Write each answer as a fraction and as a decimal rounded to 4 places. Solution. First, find the tangent of angle S. The tangent of angle S is equal to the length of the leg opposite angle S divided by the length of the leg adjacent to angle S, which is equal to RT divided by ST. Substitute 80 for RT and 18 for ST. So the tangent of angle S equals 80 divided by 18, which equals 49, or approximately 4 and 4,444 10,000ths. Unless told otherwise, you should round the values of trigonometric ratios to 4 decimal places and round lengths to the nearest tenth. Now find the tangent of angle R. The tangent of angle R is equal to the length of the leg opposite angle R divided by the length of the leg adjacent to angle R, which is equal to ST divided by RT. Substitute 18 for ST and 80 for RT. So the tangent of angle R equals 18 divided by 80, which equals 9/40 or 2,250 10,000ths.
So just as a reminder, in case you missed that, whenever you're finding that ratio, you're going to let 4 decimal places be rounded. Okay? 4. Now, that's for the ratio. If you are finding a side, which you can also do for the side lengths, we're going to round them to 1 or a tenth. Continuing on, these are the examples we'll do in our notes together. And then here's how we would find a length. If we have the angle, then we can also use the ratio to find the length.
Find the value of x. Round your answer to the nearest tenth. Solution. Use the tangent of an acute angle to find a leg length. The tangent of 32 degrees is equal to the length of the opposite leg divided by the length of the adjacent leg. Substitute 11 for the length of the opposite leg and x for the length of the adjacent leg. So you have the equation, the tangent of 32 degrees equals 11 divided by x. To solve for x, first multiply each side of the equation by x. This gives you x times the tangent of 32 degrees equals 11. Then divide each side of the equation by the tangent of 32 degrees. This gives you x equals 11 divided by the tangent of 32 degrees. Using a calculator, you get x is approximately equal to 17 6/10. So the value of x is about 17 6/10. You can also use the table of trigonometric ratios available at bigideasmath.com to find the decimal approximations of trigonometric ratios.
So again, I held up, you can have a little tiny calculator like this, or you can have a TI. You can use your phone, but you won't be able to use your phone in all situations. So if you have a little one, as long as it's a scientific calculator and it has those little buttons that say sine, cosine, and tan, those are the ones you want. So that is what you need for these scientific calculator. Otherwise, it's just basic algebra that you're going to be setting these equations up and then solving for the next one. So here's another way you can use it. You can find the tangent of an acute angle measuring 30 degrees, 45 degrees, or 60 degrees by applying what you know about special right triangles. So we talked about special right triangles before, right? If it's a 45, 45, 90, your sides are x, x, and x root 2 for your hypotenuse. If the special right triangle is a 30, 60, 90, then the short side across from the 30 is x, the hypotenuse is 2x, and then the size in the middle is x times the root of 3. So you are gonna, you can use those theorems as well, and here's an example.
Use a special right triangle to find the tangent of a 60-degree angle. Solution. Step 1. The tangents of all 60-degree angles are the same constant ratio. Any right triangle with a 60-degree angle can be used to determine this value. Because all 30-degree, 60-degree, 90-degree triangles are similar, you can simplify your calculations by choosing 1 as the length of the shorter leg. Use the 30-degree, 60-degree, 90-degree triangle theorem to find the length of the longer leg. By the 30-degree, 60-degree, 90-degree triangle theorem, the length of the longer leg equals the length of the shorter leg times the square root of 3. Substitute 1 for the length of the shorter leg. When you simplify, you get the length of the longer leg equals the square root of 3. Step 2. Find the tangent of 60 degrees. The tangent of 60 degrees is equal to the length of the opposite leg divided by the length of the adjacent leg. Substitute the square root of 3 for the length of the opposite leg and 1 for the length of the adjacent leg. When you simplify, you get the tangent of 60 degrees equals the square root of 3. So, the tangent of any 60-degree angle is the square root of 3, which is approximately equal to 1 and 7,321 ten-thousandths.
Yeah, sorry about the captions over that. Again, we're going to be able to use previous knowledge to solve problems that we had learned in previous sections. So hopefully you will be able to apply that knowledge. Again, if you want to see it, just back up or pause the video, back up, watch it again. We'll be doing some more examples under the camera as well. So these are more examples from our notes, the monitoring progress, and then this is exactly how we would solve. You've got something called the angle of elevation and the angle of depression. And so this is how we're going to solve, this is the rock wall problem that they started at the beginning of the chapter. The angle that an upward line of sight makes with a horizontal line is called the angle of elevation. So if you'll notice in this picture, 59 degrees is the angle of elevation from the ground up to whatever, to the top of whatever you're looking at. So oftentimes it's like, well, how tall is this building? You have to count, from the ground where your feet are all the way up to the building. If you count from where your eye level is, right, then you also have to count the vertical distance from where your eyes are to your feet. So it's easiest just to write like this. The other angle that we can talk about is the angle of depression. So say you're on the top of a building and you're looking down. Your horizon goes directly out, right, straight ahead of you. And if you're looking down at somebody, then the angle right there between your straight horizon and down toward wherever you're looking at, that angle is called the angle of depression. So one's elevation when you're looking up and one's depression when you're looking down. Just to make, as long as you know it's from your horizon wherever you're looking. So if you're 50 feet up, it's the angle that's down from where you're looking straight ahead. We are going to be doing a little bit of angle depression, but right now this example uses angle of elevation, as long as you realize, elevation is up, depression is down. Okay, so let's watch another one.
You are measuring the height of a spruce tree. You stand 45 feet from the base of the tree. You measure the angle of elevation from the ground to the top of the tree to be 59 degrees. Find the height h of the tree to the nearest foot. Solution. Step 1. Understand the problem. You are given the angle of elevation and the distance from the tree. You need to find the height of the tree to the nearest foot. Step 2. Make a plan. Write a trigonometric ratio for the tangent of the angle of elevation involving the height h. Then solve for h. Step 3. Solve the problem. The tangent of 59 degrees is equal to the length of the opposite leg divided by the length of the adjacent leg. Substitute h for the length of the opposite leg and 45 for the length of the adjacent leg. So you have the equation, the tangent of 59 degrees equals h divided by 45. To solve for h, multiply each side of the equation by 45. This gives you 45 times the tangent of 59 degrees equals h. Using a calculator, you get 74 and 9/10 is approximately equal to h. So the tree is about 75 feet tall. Step 4. Look back. Check your answer. Because 59 degrees is close to 60 degrees, the value of h should be close to the length of the longer leg of a 30-degree, 60-degree, 90-degree triangle, where the length of the shorter leg is 45 feet. By the 30-degree, 60-degree, 90-degree triangle theorem, the length of the longer leg equals the length of the shorter leg times the square root of 3. Substitute 45 for the length of the shorter leg. Using a calculator, you get the length of the longer leg is approximately equal to 77 and 9/10. The value of 77 and 9/10 feet is close to the value of h.
So you should always be able to estimate with your special triangles as well. That's another tool in your tool bag for excellence. Okay, so I do believe that's the end of our tangent ratio. We'll be doing one more example together under the camera, and I do believe the problem set is about 20 problems. So again, we're going to be doing a couple of notes that we will fill in class, and this should be enough to get you going.